So, yeah, this is the speaker. The next talk will be given by Dr. Sheng, Xin-Li Sheng, and he's going to talk about Casanova-Bayes approach to non-local collision term. Please, Xin-Li.
Okay, thank you. First, I want to thank the organizers for giving me this opportunity to share my work here. My talk today is mainly based on the work in collaboration with Enrico, Sheng, and Dirk. So this is the outline of my talk. First, I will briefly introduce the motivation of this study, as well as some backgrounds. Then in the second part, I will show the Casanova-Bayes equation for Wiggin function. The Wiggin function is then decomposed into 16 components. Maxwell conditions and the Boltzmann equations for these components will be also given in this part. Spin-dependent distribution is defined in the third part in order to describe the Wiggin function. For this distribution, we obtained the related Boltzmann equation, which contains both local and the non-local parts. The latter part will be summary. In relativistic high-bound collisions with non-zero impact parameter, the fast-moving nuclei carry large orbital angular momentum. Part of the initial orbital angular momentum will remain in the quark-gluon plasma and polarize the spin of quarks. This process is similar to the Barnett effect. When the temperature of the quark-gluon plasma decreases, these polarized quarks will finally form polarized hadrons and mesons. These effects were started by Zhuotang Liang and Xin-Li Wang in 2005, and later on started in many works in the past few years. Experimentally, the STAR collaboration has measured the global and the local polarizations of lambdas and anti-lambdas. The results are published in Nature and PRL respectively. Recently, they also measured the spin alignment of band mesons and K-star zero, where they found significant deviations from 1/3. A large amount of theoretical works are made for explaining these results, including microscopic models, statistic models, and spin hydrodynamics and some kinetic theories. In a vertical field, particles will for sure be polarized along the direction of rotation, and it will finally reach equilibrium. Finally reach an equilibrium state with correction from spin vorticity coupling. But how this happens microscopically is still not clear. In this work, we are aiming to derive the Boltzmann equation, which includes the transfer between spin angular momentum and orbital angular momentum. This may help us better understand the spin evolution in a vertical field. Such an equation has already been obtained using the method developed by the works. You can see Noah's talk for more details. And in this talk, I will derive the Boltzmann equation from the Casanova-Bayes equation. Here, I'm also pleased to mention some related works. The first one is from Zhang Fang and Chun Wang, Xin-Li Wang. They studied the collisions between wave packets using a quantum field approach. And the orbital angular momentum entered this system by considering a non-local impact parameter between the incoming wave packets. And the work by Yang, Hattori, Hidaka, in this work they also studied the collision term in KB equation in a systematically way. And in a paper by Ziyue Wang, Guo, and Zhuang, They also obtained the equilibrium span distribution for the endurance work. So now let's focus on the Kartanov-Behm equation. This equation is based on the two-point Green function defined on the closed time path contour, also known as the Schwinger-Cavendish contour. This contour starts from time t0 and then go to infinite future and then go back to t0 again. The Green function defined on this contour has a time ordering according to the sequence of the time arguments t1 and t2 on this contour. Since this contour has two branches, we have four kinds of Green functions as according to the position of t1 and t2, as shown in this table. If both of these two time arguments are located on the first branch, the time operator, the ordering operator TC will become the normal time order. And in this case, we have the normal Feynman propagator. And if both T1 and T2 locate on the branch 2, then TC will be an anti-time ordering. And when T1 is on branch 1 and T2 is on branch 2, we will find the T2 is always in front of T1 on this contour. In this case, we have the definition of G lesser, where psi bar x2 is always on the left-hand side of psi x1. And similarly, we have the definition of G greater, where psi x1 is always on the left. The retarded and advanced Green functions can be defined using the less operators and the greater operators and multiplying with unit time step function. For the Green function G lesser, we can take a Fourier transform with respect to the relative position x1 minus x2. The function obtained in this way is a well-known Wigner function, which is widely used in many theoretical works. The kinetic equation for the Wigner function can be derived from the Dyson-Schwinger equation. As shown in this figure, the full Green function equals to the free particle Green function d0 plus self-energy correction. Multiplying the Dyson equation with the inverse of d0, we obtain the equation for the two-point Green function g. Here, the operator in front of g is the inverse of d0, and the self-energy here the self-energy sigma and g are defined on the closed time path contour, and thus they can be written in a matrix form, which contains the four kinds of Green functions defined in the last page. Taking a Fourier transform for this equation, we immediately obtain the Kartanov-Behm equation for the Wigner function. On the right-hand side of this equation, we have some contributions from self-energy sigma. Here, gradient expansion is used, and the higher order in spatial gradient are truncated. By using the Kartanov-Behm equation can be simplified using the on-cell approximation, which says that the retarded or advanced function can be replaced by the difference between greater operator and the lesser operator. Then the KB equation is casted into a form which consists with greater and lesser G and greater or lesser self-energy sigma. And standard and widely used way to study the Wigner function is to decompose it in terms of the generators of Clifford algebra, gamma A. The expansion coefficients are all real functions in 8-dimensional phase space. And they can be computed by multiplying the Wigner function with operator gamma I and then taking trace. According to their parities and Lorentz properties, these coefficients are identified as scalar, pseudo-scalar, vector, X vector, and tensor, respectively. And they have some physical meanings such as mass density, phase space, fermion current density, and so on. The Cartanov-Frame equation can also be decomposed in terms of gamma A, just as what we did for the Wigner function itself. The real and the imaginary parts of each component are listed here. Collisions contribute as source terms on each side of the right-hand side of each equation. In collisionless case, these equations have been solved analytically order by order in these papers. So similar to the collisionless case, we also take a semi-classical expansion, which means we expand all functions, equations, and operators in terms of H bar. Then at zeroth order in H bar, the equations are listed here. With the help of them, we can express the vector and the tensor components in terms of the zeroth scalar and the zeroth order axle vector. And inserting these relations back to the zeroth order equations, we immediately obtain the Maxwell conditions for the zeroth order scalar part and zeroth order axle vector part. In this order, we find that all quantities are on the normal Maxwell because the interactions do not contribute at this order. And at the first order in H bar, we start to have some contributions from collisions. All the first order equations are listed here, and similar to the zeroth order, we can express the pseudo-scalar vector and the tensor parts in terms of first order F and first order A mu. And we also need the zeroth order components. Again, inserting these relations back to the first order equations, we obtain the Maxwell conditions for F1 and A mu 1. And on the other hand, the Boltzmann equation for the zeroth order components are obtained at this order. Similarly, the Boltzmann equation for the first order components are derived by second order equations, which will not be shown here. In this page, I have collected all Maxwell conditions and the Boltzmann equations for the scalar F and axle vector A mu. For the axle vector component, we have some constraint equations. All the other components can be expressed once we know F and A mu. And from the Maxwell conditions, we can find that the interactions will induce some Maxwell conditions at first order. The component equations shown in my talk have also been discussed in Ziyue's talk, but they started the vector component instead of the scalar component. We also have an alternative way for deriving the on-cell conditions and the Boltzmann equations. From the Cardano-Beam equation, we multiply it with this operator gamma dot d plus some with gradient part plus m, multiply it with this operator from the left-hand side, and then decompose it in terms of matrix gamma A. The real part will give us mass cell conditions for different components, while the imaginary parts are Boltzmann equations. We should emphasize that at first order in H bar, the mass cell conditions and the Boltzmann equations may have various forms. For example, the Boltzmann equation for the first order scalar part can be written in this way or in this way. The upper equation for F1 is obtained from component equations, and the lower one is derived using the method in this page. The right-hand side of this equation looks a little different, but I can show that they are equivalent at the order of the self-energy. The equivalence is proved using the adjoint Dirac equation. The right-hand side of this equation is order of self-energy. So we multiply this adjoint Dirac equation with self-energy from the right, from the left, and then integrate over the intermediate position x prime. The Claisen term in Cardano-Beam equation is obtained by taking a Wigner transform for the term in the blue box. Thus, from this equation, we can derive a constraint for the Claisen term. Here, the Claisen term is of first order in self-energy, while the right-hand side is second order in self-energy. So if the self-energy is a small quantity, the right-hand side can be neglected. Now let us see how we define the spin-dependent distribution. So we consider the case of free particles. The free Dirac field can be quantized in this way by using the plane wave functions u and v. Inserting this Dirac operator into the definition of Wigner function, we immediately obtain this result. Here, the momentum is on the mass cell because we are considering free particles and the interactions are not included. The first term on the right-hand side represents a contribution from point-like particles from quantum distributions of point-like particles. This part is widely used in literature, such as in the paper of Beccattini. The second term, on the other hand, arises from quantum non-local correlations. It contributes when we consider the wave package. And this term is also related with Barry connection in quantum theories. So in this Wigner function, we have used a matrix valued distribution, whose definition is listed here. Here, n plus or minus represents a expectation value of particle or antiparticle operators. But with A dagger and A in different momentums. This matrix distribution is a two-dimensional Hermitian matrix. So it can be decomposed in terms of the unit matrix and the three generators of SU2 group. Directly taking trace, it will give us the intrinsic intrinsic probability density in phase space, and the remaining part gives us the intrinsic spin density in particles respectively. Here I have a very simple example. We consider a well-packaged state, which can be written in terms of superposition of plane waves. For this wave packet, we can calculate the matrix value of the distribution. The result is a Gaussian type distribution multiplied with some spin part. So this is just what we expected. So we identify this matrix distribution as the intrinsic probability and spin density for this wave packet. And we found this interpretation is important for connecting massive case with massless case. Now, on the other hand, another way to define matrix value distribution is to sandwich the Wigner function between U bar and U. Here, we also introduced an additional energy integral so that we can separate the particles from antiparticles. So comparing with the intrinsic distribution F, this function G contains an additional non-local correlation. So if we consider the Gaussian type wave packet, obviously the nabla X, the spatial gradient will be proportional to X. And the term P cross nabla X is then proportional to P cross X, which is the orbital angular momentum. For the probability density, the term N dot P cross nabla X will be the contribution from spin orbital coupling. And previously, we have expressed the Wigner function in terms of the matrix distribution F. And then now we can also express the Wigner function in terms of this modified distribution G. For example, the scalar component is shown here. In this way, the non-local correlation in the Wigner function is embedded inside G. So instead of using a two-dimensional matrix, another equivalent way is to extend the phase space by introducing a continuous spin vector as mu. The integrating measure for this additional spin variable is given here, which contains two delta functions. The first delta function tells us that spin vector S mu should be perpendicular to the momentum. And the second delta function is the normalization condition for S. In particles rest frame, the S mu is a pure space vector which is located on a spherical cell. A spin-dependent distribution function is then defined by projecting the matrix form distribution onto the direction of S mu. This function can be interpreted as the probability of detecting one particle if we measure along the direction of S mu. With this function, we are able to write down the Wigner function in a simple form. And this form will be used in later discussion when we calculate the self-energy. We emphasize that the definition of this spin-dependent distribution is not Lorentz covariant because the zeroth component of the momentum has been integrated out. A similar but covariant definition has been used in other works, placed talks by Noha and Radoslav for more details. So the matrix distribution G contains both the intrinsic probability and the spin density. And it also contains some contribution, non-local contributions, which depends on the spatial gradient. So here we can cast the span-dependent distribution function into two parts. And the second part is now from non-local correlation, and it is written in terms of spatial shift delta mu times some spatial gradient of the local part. Here S mu is the phase space variable S mu is normalized with the constant C0 is taken to 1. Otherwise, the download term will be more complicated than this form. So the total G plus is then can be expressed using the local part only with the additional shift delta x. Here the space shift, the shift delta x mu, its zero sum, its time component is 0, and the space component proportional to the 3 momentum p times spin s. And obviously this delta x is of order h bar, first order in h bar in our power quantity. And on the other hand, the local part in general also contains both zeroth order in h bar and the first order in h bar. So here and here I mainly focus on the definitions of particles labeled by the subscript plus. But for antiparticles, the definitions and discussions are similar, which will be given in our upcoming paper. So in the next part, I will show the Boltzmann equation for the span-dependent distribution. In the evidence of interactions, the span-dependent distribution can be derived from the Wigner function by using a spin projection operator. The anti-integration takes out the particle part and drops the antiparticle part. We also assume that this relation holds even when we have interactions between particles. I think this is possible if we consider the dilute gas approximation. That is to say, collisions are rare and happen in a very short range. And the particles behave like free particles between collisions. From the equation of Wigner function, it is easy to obtain the Boltzmann equation for the span-dependent distribution D plus. Here the collision term is given by products of self-energy and the Wigner function with the same phase space argument. And the self-energy can be obtained by considering the following diagrams. At a leading order in Copley constant, the diagrams will give us some mean field contribution. In this work, we neglected this mean field contribution because we are more interested in scattering processes. And at next to leading order in Copley constant, we have these two Born diagrams, the direct diagram and the exchange diagram. They will give us contributions from scattering. In these diagrams, solid lines are propagators of fermions and wave lines are propagators of bosons. We take the NDL model as an example. This Lagrangian contains various kinds of 4 fermion interactions. where gamma A is a matrix product of Dirac flavor and color matrices. And its subscript A labels different kinds of interactions, such as scalar interaction, pseudo-scalar interaction, and so on. GA is the related coupling constant. Using the Feynman rules of this NGL model, we can write down the self-energy for the point diagrams. It is expressed in terms of G lesser and G greater. Now let's go back to the Boltzmann equation. The Cauchy term contains the self-energy sigma, and as we just shown, sigma is a function of G lesser and G greater, and G lesser and G greater can be expressed using the distribution function small g plus. So the Boltzmann equation can be written in a form that only contains function g. The Cauchy term here is very similar to the spinless case, and its structure is very clear. It contains a delta function which ensures the momentum conservation. And the last line in the Cauchy term is related to the amplitude squared for the scattering processes. Its implicit form is a little complicated. In this amplitude, the incoming and outgoing particles carry spin S1, S2, and S3 and SP respectively. And all possible spin configurations are considered because here we have an integration over all spin variables. And the third line contains products of distribution functions. Here, G1, 2, 3, and Gp represents spin-dependent distributions for particles with momentum P1, 2, 3, and P.
Xin-Li, you only have 2 minutes.
Yeah, okay. The third line contains both the gain part and the loss part, and that's the one is at local equilibrium. And the cancellation between gain term and the loss term gives us the detailed balance condition. The distribution in our SPAR counting, the distribution function can be expanded into a zeroth order part and the first order part. We assume that the zeroth order distribution does not depend on spin. So from the detailed balance condition, we find that the zeroth order at equilibrium gives the Fermi-Dirac distribution, or the Boltzmann equation if we consider the Boltzmann limit. And the first order in SPAR, the distribution function will, on the other hand, will contain some spin vorticity coupling. So in general, this G+1 can be divided into a spin-independent part and a spin-linear part. And we can also parameterize using a vector spin potential mu as alpha, or using a tensor spin potential omega alpha beta. These two ways are equivalent. So we have a relation between mu as alpha and omega mu. The spin independent part at the first order in general can be set to 0 because it can always be merged together with the zeroth order part. And on the other hand, despite the function G+1, there also exists a non-local contribution at the SPAR order. In the Boltzmann limit, the zeroth order distribution is the Boltzmann distribution. So it is possible to calculate the spatial derivative of G0. So at this order, the detailed balance condition is shown as the one in this box. And this condition has been obtained using the growth method in our published paper. Here we reproduce it using the Karnoff-Behm equation. So at global equilibrium, the spin chemical potential equals the spin potential equals minus of some vorticity, and the killing condition is satisfied. In this case, the detailed balance condition is equivalent with the angular momentum conservation. Here, h power over 2 times the sigma mu u is the spin angular momentum, and the delta x mu p mu minus delta x mu p mu is the orbital angular momentum. Terms in premises are total angular momentum for incoming and outgoing particles, respectively. So here is a brief summary of my talk. In this work, we obtained the Maxwell conditions and the Boltzmann equations for different components of regular function using the Karnoff-Behm equation. The wave function can be expressed in terms of matrix value distribution, and also it can be expressed in terms of spin-dependent distribution function. This distribution contains non-local correlations. We calculate the self-energies for point diagrams, including the direct diagram and the exchange diagram. Using the self-energy, we derive the explicit form of Boltzmann equation for the distribution function G+. And the detailed balance condition is discussed in this work, where the non-local correlations appear as a contribution from orbital angular momentum. In most parts of this talk, we only consider particles, and antiparticles will be included in our upcoming paper. Okay, thanks for your attention.
Okay, time for discussion. Any questions or comments? Shuai, please.
Hi, thanks for the nice talk, Xin-Li. Basically, I would like to ask, what's the definition of the X in this situation? Because it looks familiar for this delta X mu for me, because simply use the Dirac equation, calculate a Gaussian wave packet average of the position operator, it will give this delta X mu. So how you get this delta X mu? What's the definition? How that basically is a canonical X mu, or say you using some other definition of the position?
I mean, the delta X comes from this non-local correlation. This nabla Q x on U bar U, and we can project this. I mean, this part. This nabla Q, U bar U, this part is a matrix in spin space because this U bar has spin index S and this U has spin index R. So this part is a matrix in spin space. And then we project this matrix onto the direction of S as we did here in this way. Just replace the T using that nabla Q, U bar U, that term. Then it gives us the delta X mu. Right? That's it.
Okay,
I think it's maybe it's similar with side jump.
Yeah. Basically, I think from what I see, it seems like this is basically the canonical definition of the position. So, but I just say that if you use that kind of thing, then when you do the boost, then this kind of definition of the position will kind of transfer kind of non-trivially. Basically, when you do the boost, or say if you change it to other frame, then your change of the coordinate or say change of this x mu probably will mix with the side jump contribution. Indeed, you can define something to remove this delta x mu if you follow the word line of the particles. So I just mentioned probably
there may be some problem when we take a Lorentz boost, but in this work we have fixed the frame, and actually this definition is not Lorentz invariant because it only depends on the stream momentum. So yeah, it's a good question. The Lorentz invariance is a good question, I think, but we did not consider that in this work.
Okay, thanks. We can discuss later. Okay, thanks.
Yeah. Thank you.
Any other questions or comments? Okay, I cannot see any. Yeah.
Yeah,
Please.
sorry, just a short question. So you and Nora are arriving at the same result, right? Just with different methods. Yeah. Okay, good. Good. Just for me to clarify. Thank you.
Yeah, this is from the KB approach, and Nora's approach is the Groot method for Wiener function. So actually, we can get the same conclusion.
Are there situations where the two give different results, or does one expect them to give the same result? I'm sorry for the ignorance. I'm not an expert.
Sorry, can you repeat your question, please?
If you find that you get terms which are different, does this mean that someone made an error, or there are situations that the results will be different, that you expect the results to be different?
Yeah. Well, I think we have obtained the same results, the same Gaussian equation, and also both of them we derived this detailed balance condition. But actually, we are not sure why these two properties matches. We are trying to prove they are equivalent, but it's still an ongoing work.
Okay, thanks.
Okay, thank you.
Okay. Any other questions? Yeah, I cannot see. So then yeah, thank Xin-Li again. Then I stop recording.